4, 1, 2. So this is minus 2. So now you are having a situation plus 1 and minus 2. So it means you will be requiring 2 rotations. One rotation will be at the child and another rotation will be at the parent. Now child is what is it? Yeah. So child is plus 1. You want to reduce the gap, so you like to make child minus. Making minus means rotating towards right. So let us rotate the child towards right. So what will happen? This is the child. This will be rotated towards the left. So like this. And next time parent will be rotated. So see, first time I am not disturbing the top. What is top? 4 is at the top. What should we write it downwards? 4 is at the top. This side is 3. This side is 2. This side is 1. And this side is. Now this side, who will come at the top? 7 will come at the top. Who will be right of the 7? 9. Right of the 9? 10. And right of the 10? 11. Okay. Now 7 has been rotated like this. So right. So what will come at the left of the 7? See, left of the 7 is rotated like this. 9. So left of the 9 will be 8. And this side you have 6. And this side you have 5. Okay, so earlier right of the 7 was 8, but now since 9 is coming at right of the 7, so 8 will go to the left of the 9. Okay, is this was clear to you? Now calculate. This is 0, this is minus 1, this is again minus 1. 1, 2, 3, 4, 1, 2. So this is how much? 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2. This is how much? Minus? Say something. Minus? 1. This is 1, 2, 3, 4. 1, 2. So this is minus 2. So what will happen next time? Okay. Redraw. 7 will be at the top. Left of 7 will be 4. Right of 4 will be 6. And then 5. 5 is always the left of the 6, so there is no problem. This side is, I rotated like this. This side is 2, this side is 1, this side is 3. Okay, 7 is at the top. What is this side? 9. What is this side? 8. What is this side? 10. And what is this side? Okay, now this is a balanced tree. Only thing you need to remember, when there is a difference of 1, then from child rotation is to the parent. Whenever it exceeds 1, whenever it becomes plus, suppose it is plus 1 and plus 2 situation, minus 1 or minus 2 situation. If it is plus 1 and minus 2 situation, then difference is 2. So first rotation will be from grandchild to child. Okay, and the second rotation will be from child to parent. Okay, is this clear to you? So I hope now you have some understanding of the things. Where is the boy who raised question yesterday? Where is he? Yes, gentlemen, how are you? Are you understanding a little bit? Okay. Let's move ahead now. I just try to throw some light on a sparse matrix. S-P-A-R-S-E. What is sparse matrix? Okay, So let us draw a matrix of order 2, 2 into 2, that is order 3, 3 into 3. Suppose I am having a 3 into 3 matrix like this, 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay, so we make it 4 into 4. We require some more fun. Order is 4, 4 into 4. So this type of matrix where majority of elements are 0. So this type of matrix is called a sparse matrix, sparse array. Okay, so sparse array or sparse matrix is a matrix or array where majority of elements are 0. Normally, whenever we store elements of a matrix, how do we store elements of a matrix? Normally, this is okay. This we have assumed that things are in rows and columns. Things may be straight also. Okay. So what are you storing? You are storing row number, column number, and element. Row number, column number, and element. So how many entries will you have in normal matrix representation? There are 4 rows and 4 columns. In total, there are 16 elements. So you will have row number, column number, and element. How many places? 16 places. But sparse matrix is a matrix where majority of elements are 0. And what is the sparse representation of a matrix? Okay, so in sparse representation of matrix, in sparse representation of the matrix, we represent only non-zero elements. We represent only non-zero elements by using triplets. We represent only non-zero elements by using triplets, and all other elements are assumed to be zero. So we represent only non-zero elements and we assume that all other elements are zero. So what would be the see, if we are going for a normal representation, so we require representation for 16 elements. Now if we go for sparse representation, I will require representation for only 4 elements. I will say row number 1, column number 0, element is 1. So I just have this type of representation. I say row number 1, column number 0, element is 1. Then row number 2, column number 0, 1, 2, element is 1. 0, 1, 2, 0, 1, 2. Then row number 3, column number 1, element is 1. Then row number 3, column number 0, 1, 2, 3, element is 1. Okay. So if I want to use sparse representation, then how many entries will I have? I will have 16, and every entry involves 3 things: row number, column number, and element. So instead of, if the majority of elements are 0, I am representing only non-zero students. Suppose in this class, suppose I take class tomorrow also. It is possible taking a class tomorrow. Do you have examination tomorrow? No, so a class can be taken tomorrow. So if I take a class tomorrow and suppose there are only 10 students present. So while taking attendance, what will we do? Normally what we do, we note the names who are absent. If only 10 are present, okay, to save time and memory, what we'll do, we'll have representation for only those students who are present. All others will be deemed to be absent. Okay, so same way there, this is called sparse array. See, next is garbage collection. Garbage collection. You must have dynamically allocated memory. You must have used malloc or calloc function. That function, what do those functions do? Basically allocate memory for a particular type and then return a white pointer. Okay, so you prototype externally typecast it and that is assigned to a pointer. Okay, so memory is allocated and its starting address after typecasting is allocated to a pointer. You know this much? Okay, now what happens afterwards? Suppose you lose the pointer. This is a classroom, suppose there is a pointer P at the start. So I don't know address of any student, I only know the address of first. Suppose I use address of first student, then what will happen? So elements are existing, but you are not able to access them. Or I say the programmer will lose control of the element. Suppose we do have a linked list like this. And P is a pointer pointing at the start of the linked list. Now if I lose P, then what happens? That linked list is allocated in the memory, but the programmer has lost control of it. Okay, so these type of things are called garbage. Okay, so you want to write garbage collection. When a programmer loses pointer, inside bracket you write address to a memory allocated, When a programmer loses a pointer to memory allocated, then he can no longer access that memory. He can no longer access that memory. He can no longer access the memory, although memory is still allocated. Although the memory is still allocated. Although the memory is still allocated, but the programmer has lost its control. So this type of memory, which is allocated and programmer has lost its control is called garbage. Next para you write all the operating systems as well as modern day compilers, as well as some of the modern day compilers have routines to collect that garbage, and release it so that it is available for further use. Collect it and release it so that it is available for further use. Okay. In early days, only garbage collection was the scope of operating systems only. But nowadays, modern day compilers, some of the modern day compilers, they also have their own garbage collection routine. Time to time they run garbage collection routine, so that whatever garbage is there, that is collected and released. Okay. Once it is released, where does it go? It goes to the list of memory, okay, available in operating system. Operating system maintains a list of memory available. Okay, next para. Different garbage collection routines are available. Different garbage collection routines are available. We are discussing one of the simplest one, consisting of two phases, marking phase and collection phase. Okay, so our garbage collection routine will have two phases. One will be called marking phase and second one will be called collection. In marking phase, all the memory which is allocated and pointed by external pointer, all the memory which is allocated and pointed by external pointer is marked. In collection phase, all the memory which was allocated but is unmarked, all the memory which was allocated and is unmarked is released and added to available list of memory. Okay, because the operating system always maintains a list of available list of memory of operating system. Suppose what happens, I allocated space to all of the students inside this class. Okay, I said Ramlal, you sit here, Mohan, you sit here, Ram, you sit there. Okay. But after some time, I remember, and I am interacting with only few students. All other students are meaningless for me. I lost their addresses also. So what I do? In marking phase, I mark those students, those who are of my youth. I know their address, I mark them. And then in collection phase, I say, all the students who are inside this class but are not marked should be collected. Ram, Mohan, Geeta, Sita, you stay inside the class. All other students, other than Ram, Mohan, Geeta, Sita, should go out of the class. Is it clear to you? So this is called garbage collection. Do you know something about dangling pointers? You already know about dangling pointers? Okay. All of you know about dangling pointers? All of you? Okay, fine. So now next thing is, we have to discuss something about shortest path algorithms, and we wanted to discuss Dijkstra's algorithm for finding shortest path. Dijkstra's J silent. Dijkstra's algorithm for finding shortest path. Or you may say Dijkstra's algorithm for finding shortest path from a source node to all other nodes. Okay, this is used to find shortest path from source node to all other nodes. Okay, so let us see how does it work. Suppose a graph is given to us. This is a graph given to us, and this is a weighted graph, so these are the weights. These are the weights, and our source node is A. A is our source node, and we want to find shortest distance to all other nodes from source node. Okay, 0, 1, 2, 3, 4, these type of things. So with correction, this becomes 0, this becomes 1, this becomes 2, this becomes 3, and this becomes. And our source node is this. What we can do, we can say initially source node is assigned a distance 0 because distance from 0 to 0 is 0. And all other nodes are assigned a distance infinite. All other nodes are assigned a distance infinite. To add some fun, let us have a path here also. And maybe the cost of this path is 20. This is 20. Let us, because afterwards we'll have to track it also. So let us have a origin matrix. Initially 0 is originating from 0, 1 is originating from 1, 2 is originating, because we are assuming all are isolated. And 4 is originating from 4, because initially we are assuming that all are. Any problem up to here? So this is origin matrix. What we have done, we have assigned infinite distance to all other nodes. See, whenever you will be programming, you can't assign infinite. So you will be assigning a big number, say 99999, some big number. Okay? Now starting from the source node, let us see where can we directly reach from this source node. From 0 we can reach to 1. What is the cost of reaching to 1, or what is the distance from 0 to 1? Distance is 10. Is 10 smaller than infinite? So I'll update it. I'll say now my new distance is 10, because I can directly go from 0 to. I can directly go from 0 to 3. Okay, my earlier distance of reaching to 3 was infinite, but now it will become 20. Same way I can go from 0 to 2 and my distance will become. Okay, so this is called releasing the distance. You always like to release the distance, while like to make it smaller. Is it okay up to this point? Are you comfortable? Okay. Now I have done everything from 0, so 0 is decided. So we have reached to 1. We have reached to 1 from where? From 0. So I'll update this. 1 we have reached from 0. 2 we have reached from 0. And 3 also we have reached from. Okay, this is all over for 1. So one iteration is over. Okay, all these are greedy methods. Okay. What is greediness? How many of you are greedy? What is greediness? Greediness says, whatever I am getting right now, suppose I want to have this much. Whatever I am getting right now, let me take that. Then let me try for more. Then let me try for more. That's what I am doing. This is a greedy method. Earlier the distance was infinite. Finite distance you are not getting in one shot. Okay, we have just taken from 0 and whatever you can optimize, you have optimized that. All these are optimization methods. So your 𝐒𝐭𝐵𝐮𝐜𝐿 algorithm and your Dijkstra algorithm and we were seeing that 𝐒𝐭𝐵𝐻𝐿 algorithm, all these are greedy algorithms. Okay, there is one more thing which is called divide and conquer. What is there in divide and conquer? See your binary search. You are dividing the elements into smaller things. Okay, so I give you a diagram also after this for divide and conquer. Okay, after some time in next semester you will study about dynamic programming also. Okay, so this is a greedy method. So now 0 is fixed. Now which one is the smallest amongst all? 2 is the smallest one because it has been assigned a distance 5 or it has been assigned a cost 5. Cost means distance. 5 is the smallest distance because 1 is having 10, 4 is still infinite, 3 is having 20, so the smallest one is. Earlier also we selected the smallest one, we have selected 0. So now we will be selecting 2. See, distance up to 2 is 5. We have started from source node 0, distance up to 2 is 5. Now from 2 I can go to 1. Up to here distance is 5. If I want to go to 1, I will be adding 4 more. So distance will become 9. Is 9 smaller than 10? Yes, so I will update it. Okay, so earlier I was going to 1 from 0. Now I am going 1 from 2. So now I am going 1 from 2. Is there any problem? See, earlier from 0 I was going to 1. Sorry, from 0 I was going to 1 like this. Now I am going like this. Okay, like this, this and this. So what I have said, if I want to track from where I am reaching from 1, so 1 I am reaching from 2 and 2 I am reaching from. You can see here, 1 I am reaching from 2 and 2 I am reaching from 0. So this is for tracking purpose. Any other distance which can be relaxed from 2 will not be going back to 0. Okay, 0 is already processed. Anything else? If I go to 2 to 0, see 0 is already fixed. Okay, so I have started my journey from 0 only. Why will I like to go to 2 to 0? I can go from 2 to 3. Up to 2, the cost is 5. I will add 6 more, so it will become. Anywhere else I can go from 2? No? Fine. So now 2 is also fixed. So we have said that 3 we have reached from, now we have reached from. Next time, which one is the smallest? 11, 2 and infinite. Which one is smallest? 11, 9 and infinite. So 9 is smallest. Yes. These two are already processed. So if I want to go to 3, what will be the total distance? 9 plus 9 is 18. I am already sitting at 11, so I will not consider it. Now if I want to go from 1 to 4, so what is the distance? Up to 1 is 9 plus 2, that is 11, and 11 is smaller than infinite, so I will be writing 11 here. and I'll update also. I'll say 4, I am reaching from. Okay, now next time what is remaining? You can take any one of these two. Suppose you are taking 3 next time. Now distance up to 3 is 11. If you go to 4, then you will add 3 more. So that will not make any sense. So there is no change. Okay. So these are the distances. See, from 0 distance to 2 is minimum distance to 2 is 5, and you are whenever you are going to 2, you are going directly from 0. Now if you want to go to 1, so 1 you are going from 2, and 2 you are going from 0. So you can track from there. 1 you are going from 2, and 2 you are going from 0, and what is the distance? 9. You are not going directly from 0 to 1, otherwise the distance will be 10. So you are going 1 from 2 and 2 from 0. That you can track from this original matrix. Okay, same way, if you want to go to 3, then 3 you are going from 2, and 2 you are going from 1. 2 you are going from 0, that is 2. 2 we are going from 0. Okay, we have written 0. 0 is there. So if you want to discuss about 3, so 3 we are going from 2, and 2 we are going from 0. And what is the total distance up to 3? From 0 to 11. And if you want to go to 4, so 4 we are going from 1, and 1 we are going from where? 1 we are going from 2, and 2 we are going from 0. 4 we are going from 1. 1 we see 4 we are going from 1. 1 we are going from 2, and 2 we are going from 0. So in this way you can track and you can find. This is called shortest all pair shortest source to all other pair shortest path. Okay, shortest path from source node to all other nodes. Please remember, this Dijkstra's algorithm will not work for negative weights. Okay, and it won't be able to find a negative cycle also. Okay, if you want a better algorithm who should be able to find negative cycle, first of all you should know what is a negative cycle. If you want to do that, then there is one more algorithm which is called Bellman-Ford algorithm. And in my YouTube lecture, I have explained Bellman-Ford algorithm. So we are not teaching Bellman-Ford algorithm to anybody, but we will be asking it. What you have to do, you have to see my YouTube lecture on Bellman-Ford. You will be getting a Bellman-Ford algorithm, which will be working for negative cycles. Okay, so what is your this divide and conquer? 3D algorithms I told you. What is divide and conquer? You are using in binary search, you are using in merge sort, quick sort. So what is that? Divide and conquer. See, suppose you are having a problem. This will be divided into smaller problems. Smaller solutions, and then finally we will come up with a solution. See, you solve a problem. If I ask you to find the largest of n elements, so what are you doing there? Largest of n elements. Is it greedy or is it divide and conquer? What is it? First of all, I met him only. I said he is the pig. Then I am getting opportunity to meet others, and I am changing my way. So this type of algorithm is it. Are you understanding or not? Anything else you like to ask? This is completing your syllabus up to here. And let me tell you, this is only 1% of data structure. Data structure is a very vast field, and I am learning it for last so many years. This is my 33rd year of teaching, and I started learning data structure from third year of engineering. So 2 years there, also 33 plus 2, 35. I am learning for 35 years. Okay, new algorithms are coming. How will you implement this particular algorithm, Dijkstra's algorithm? What will you use? Which data structure will you use for implementing Dijkstra's algorithm? Yes, Nirmal. Again, we will be using a VB. Okay, so in many first, the smallest thing will be at the top. You expect it. Then amongst the remaining smallest thing will come at the top. So you will be using mini only for this algorithm. And for tracking the path, okay, you require a parent matrix or you require a origin matrix through which you can track from where, okay, X I have reached from Y, Y I have reached from Z, and that you can find. Okay, so we will be asking you programs because first of all you are having your practical. First of all, in every practical we have a write-up, because at times what happens, examiner takes Viva but he is not able to do justice with you. There are so many students. So what we have done, we have split some of the marks of Viva to a write-up. Or it may be your birthday also that you could not solve, your program could not run on that particular day. Okay, so that will be a savior. What is that? Written. Where will be asking you, there will be a written test, objective type of test. Where will be asking you all basic things. Okay, and that will tell us in how much deep water are you. And then teacher's Viva will be there and your practical result will be there. Okay, so all will be as such. For getting good marks, suppose you want to get 100 out of 100. In data structure, it is possible to get 100 out of 100. If your write-up is 100% right, you are able to run the program, maybe you get 100 out of 100. You may get 0 also. So both extreme cases are available. But we are asking you Kruskal's algorithm this time. And if we ask you Kruskal's algorithm, then there will be no other. Otherwise, we ask you one smaller and one bigger, two type of problem. If Kruskal is there, that will be the only problem. If you are not able to fully solve Kruskal's algorithm, we will see whether you will be able to store a graph or not. Have you written union find or not? So based on that, we will be deciding. Okay. But if you are not able to store a graph also or implement anything like that, we will be happy to figure. See, anybody who is not helping himself, we should also not help. Okay. So what is the USP of graphic error? USP of graphic error. Unique selling point. What is that? What is USP of graphic error? Our students, we pay emphasis on practicals. We are very serious in practical examinations. If our students are bad in practical, we fail them. So our students become practically tough. In other institutions, okay, they have instructions and in practical you give maximum marks. So that does not happen in graphic. If you are having a practical of electronics, you must be having practicals of electronics also. Okay, in electronics, suppose you have a practical, and if you are not able to draw the circuit diagram, or if you are not able to tell the characteristic, suppose you are doing PNP transistor or something, and you are not able to draw the graph, you are not able to tell the list of equipments which will be required in practical. Okay, we have all reasons to fail you. Okay, but if you have done everything right and by chance you could not get result, we consider that also. But for that we see the entire process. At times things do not work out. See, in all other days you were performing that experiment quite well, that day you could not perform. But then your write-up will be okay, your list of equipments will be okay, your graph characteristics will also be okay. I think whatever I wanted to convey you, I have conveyed. Okay, fine. I wish you all the best. I will be taking a photograph with you. See, this photograph is for your reference that I have taught you today. And after 20 years, it may be for my reference also that Mr. XYZ has become, or Miss XYZ has become very big, and I taught her. Time changes very fast. Okay, let us be optimistic.